Hello everyone. Thank you for taking the time to review our final project. Our team, Padma Rao, Venkata Topuri, Manisha Karin, and Boini Bhavani, built a complete cloud-based predictive maintenance system for PowerPlant machinery. This project integrates IoT concepts, machine learning, and a dashboard interface to mimic how modern energy systems monitor turbine health in real life. Our system models how turbine sensors, a gateway, and a machine learning model work together to predict active power. Instead of costly hardware or cloud IoT devices, we created a fully software driven pipeline. This allowed us to focus on the workflow, correctness, and engineering principles behind predictive maintenance, exactly the emphasis outlined by our instructor. Wind turbines generate large amounts of data, and their performance depends heavily on environmental conditions. S- Sudden shifts in wind speed or direction can reduce power output or even cause mechanical strain. Failures are extremely expensive, so predictive maintenance is essential. However, real hardware simulation requires sensors, microcontrollers, and cloud IoT services which are beyond the scope of one semester project. Our motivation was to build a simulation that behaves like a real industrial system while staying lightweight, fully software based, and easy to demonstrate. Here is the workflow of our system from end to end. First, a sensor simulator generates turbine readings. Second, the virtual IoT gateway stores these readings as the latest sensor packet. Third, our machine learning model reads the data and predicts the turbine's active power. And finally, the dashboard displays predictions, model performance metrics, and feature importance. This pipeline reflects a realistic Industry 4.0 predictive maintenance structures: sensors, gateway, ML model, dashboard. Our functional requirements define what the system must do. These include uploading turbine datasets, simulating sensor readings, storing live sensor packets in the gateway file, predicting active power, displaying model matrices, and visualizing feature importance. Each of these features maps directly to real workflow in energy analytics and IoT data engineering. Our non-functional requirements focus on system quality rather than features. These include reliability, low computational overhead, fast prediction time, a clean and intuitive UI, and accuracy of the machine learning model. By using a random forest regressor, we ensure excellent performance with low latency, ideal for real-time predictive systems. As we refined the project scope, we made several intentional design choices. Originally, we considered physical hardware sensors, cloud IoT gateways, and user account systems. However, these features were unnecessary for demonstrating the core workflows the instructor emphasized. Instead, we implemented a software based sensor simulator, a local virtual gateway using a CSV file, and a streamlined dashboard. This preserved all costs and effective workflows, reduced complexity, and allowed us to deliver a clean, reliable system within the semester. While many projects use multiple user roles such as admin instructor or student, our system is different. This is not a multi user portal, but it is a mission driven engineering pipeline. Our roles are actually system components. The sensor simulator acts as the data producer, the IoT gateway acts as the system state manager, the machine learning model acts as the decision maker, and the dashboard acts as the user facing view. These components communicate with each other just like user roles would in a traditional app, satisfying the requirement for demonstrating workflows, state changes, and cause and effective interactions. Our system supports several important use cases. Users can upload a Tubeman datasets to validate structure and preview data. They can simulate live sensor readings. They can send the sensor packets to the virtual gateway. They can run the ML prediction engine to generate active power values. They can view model metadata including R square, RMSE, and feature importance. They can repeat this follow workflow multiple times with different sensor inputs, demonstrating dynamic system behavior. This use case formed the basis of our 25 minutes demo. Our full code base, including the machine learning model data, pre-processing scripts, gateway logic, and Streamlit UI, is available on GitHub. This ensures transparency, reproducibility, and version control best practices. We also deployed a complete dashboard to Streamlit Cloud. This makes the system accessible from anywhere and it demonstrates real-time inference directly in the browser. Now that the presentation portion is complete, we will move into the full demonstration where we walk through each use case step by step. Hello, this is the demonstration portion of our cloud-based predictive maintenance system for PowerPlant machinery. In this demo, I'll walk through the entire application exactly as the professor described. I will explain each action before performing it, show pre-existing system data, run our workflow step by step, and repeat the process using new data to demonstrate system consistency. Before I start executing the workflows, I want to walk through the structure of our application. This dashboard is the core interface of our system. We are not using multiple user roles such as admin or standard user because the system is not portal used by people. It's a pipeline based engineering system. The roles in our application are the components of the pipeline: the sensor simulator, the virtual IoT gateway, the machine learning model, the dashboard. The di- this directly satisfies the professor's requirement of showing cause and effect data flow, even without having traditional login based roles. Now I will scroll slowly from top to bottom so you can see each set. Here is the dataset upload area. Below that is the sensor simulation area. Next is the virtual IoT gateway, which is where sensor data gets stored. Then we have the model prediction area. And finally, the model metadata and feature importance visualization. Before simulating new sensor data, I will walk through the system using the existing model data. Now I will demonstrate the dataset upload capability of our system. This feature supports operational flexibility and transparency. Even though it is not strictly required for the prediction workflow, in real industrial predictive maintenance environments, operators often need to load new batches of Tuberin logins, inspect recently collected sensor data, or audit historical datasets. The Dataset Upload tab allows users to import any wind turbine CSV file with the correct structure, including wind speed, theoretical power, and wind direction and active power. Once the file is uploaded, the system processes it in three steps. It reads and validates the CSV format. It displays the data so that the engineer can verify the content. It prepares the columns for analysis or potential retraining. This aligns with modern MLOps workflows where versioning, data review, and retraining triggers are common. Even though our project focuses on prediction rather than retraining, supporting dataset upload adds completeness and realism to our pipeline and matches the professor's expectation that a good project should support evolving data requirements. This represents pre-filled or pre-existing information, similar to the professor's example. of logging in and seeing previously created assignments. The reason for having this is if this project is used to be used for another plan, then I will not scroll to the metadata section. Here we can see the model features. The system was trained on three features: wind speed, theoretical power, wind direction. Here are the dataset sizes. Training is around 40,000 rows. Testing is around 10,000 rows. Here are the model's performance matrices. Training is 0.936. Test R2 is 0.911. Training RMSC is around 330. Testing RMSC is around 389. These metrics show that our model is both accurate and stable. Now I will show the feature importance table. Theoretical power has the highest importance, followed by wind speed and wind direction, has the smallest contribution. This visualization provides the same kind of insights an admin dashboard would provide, but it's internal to the system rather than role based. Next, according to our use cases, we support dataset upload. This is not required for prediction, but we include it to support exploration and validation. Now I will upload a sample wind turbine dataset. I will click Browse Files, select the CSV and upload it. The system automatically interprets the file structure. This step mirrors the professor's example where pre-existing data is shown before creating a new data. This also simulates what an operator or engineer would do before retraining or auditing the model. Now, I will simulate the system workflow. Before performing any step, I will say what I am about to do, so the grader clearly understands the intention. First, I will simulate live sensor readings for wind speed, theoretical power, and wind direction. I will set wind speed to 10 ms, theoretical power to 1500 kW, and wind direction to 150 degrees. Now, I will click Simulate Sensor Data. This generates a live sensor packet. Next, I will send this packet to the virtual IoT gateway. This gateway acts like an edge IoT device. It stores the most recent sensor reading in a CSV file. This is the equivalent of the professor's example where an admin action updates a system value. I will now click Send Data to Virtual Gateway. The system writes these values to gateway underscore data slash latest underscore sensor.csv. Next, I will run the machine learning model on the gateway's latest reading. I will click Predict Power Output. The model loads, reads the gateway's CSV and outputs the predictive active power. Here's the predicted turbine output for these conditions. Now, I will repeat the workflow using completely different values to show that the system functions consistently. Just like the professor's example of posting a second assignment from the different user perspective. I will change the sensor readings to represent a lower wind scenario. Wind speed is 6 ms, theoretical power 700 kW, and wind direction is 90 degrees. Simulating sensor data now. Now, I will send the new packet to the virtual gateway. You can now see the gateway CSV updated with the new readings. Now I'll run the prediction again. This is the new predicted power output. I'll now perform a third full workflow. This one represents a high window scenario. I'll set very high window conditions to show how the model responds to the upper limits. Setting window speed to 18 ms, theoretical power to 2500, and wind direction to 175 degrees. Simulate sensor data. Send to gateway. Here we can see the gateway updated with the high wind data. Now I will run the model prediction again. And here is the predicted active power under these extreme conditions. Now I want to address one requirement from the assignment demonstrating the difference between user views and admin views. In our system, the roles are not human based, they are component based. Instead of switching between admin and user accounts, we switch between sensor simulation, gateway storage, model inference, system metadata. This aligns with the professor's requirement of showing data flowing from one part of the system to another and updating dynamically. Just as an admin would see updated user data, here we show updated gateway data, updated predictions, and updated system insights every time new sensor data is entered. Traditional user roles do not apply to our pipeline style system, so we instead demonstrate system state updates across components which fulfills this same educational purpose. To conclude the demonstration, I will summarize the full workflow end to end. The user simulates sensor data, the system packages them as a sensor data. The packet is sent to the virtual IoT gateway. The gateway automatically updates the system state. The machine learning models reads the gateway data and predicts active power. The dashboard renders prediction, metadata, and visualizations. This completes a full Industry 4.0 style predictive maintenance cycle. We demonstrated this workflow 3 times with different conditions to show system consistency, reliability, and reactivity exactly matching the professor's requirements for cause and effect demonstration. Thank you. Now I want to address one requirement from the assignment, demonstrating the difference between user views and admin views. In our system, the roles are not human based, they are component based. Instead of switching between admin and user accounts, we switch between sensor simulation, gateway storage, model inference, system metadata. This aligns with the professor's requirement of showing data flowing from one part of the system to another and updating dynamically. Just as an admin would see updated user data, here we show updated gateway data, updated predictions, and updated system insights every time new sensor data is entered. Traditional user roles do not apply to our pipeline style system, so we instead demonstrate system state updates across components, which fulfills the same educational purpose. To conclude the demonstration, I will summarize the full workflow end to end. The user simulates sensor readings. The system packages them as a sensor packet. The packet is sent to the virtual IoT gateway. The gateway automatically updates the system state. The machine learning model reads the gateway data and predicts active power. The dashboards renders predictions, metadata, and visualizations. This completes a full Industry 4.0 style predictive maintenance cycle. We demonstrated this workflow 3 times with different conditions to show system consistency, reliability, and reactivity, exactly matching the professor's requirements for cause and effect demonstration. Thank you.